Hi, I'm Cora, and this is Gabby, and we worked on an inhaler aid for our project. For many asthma patients, using an inhaler isn't just about knowing how, it's about physically being able to use it. While up to 70% of patients use inhalers incorrectly, this is not always due to poor technique. For individuals with arthritis, reduced hand strength and joint mobility can make it physically difficult to use an inhaler. In one study, only 53% of rheumatoid arthritis patients were able to properly depress the inhaler canister, compared to 91% of healthy individuals. However, this challenge is not limited to patients with arthritis. Many individuals, including older adults, patients with Parkinson's disease or ALS, and those with reduced grip strength or limited dexterity, may face similar difficulties when using standard inhalers. This problem could lead to inadequate medication delivery, worsening symptoms, and increased reliance on medical assistance. To address this gap, we developed an ergonomic inhaler attachment that uses a lever-based mechanism to improve grip and provide a more stable and accessible way to use a meter-dosed inhaler. We call this device the HandyHaler. We used Autodesk Fusion to design our prototype. This body piece is designed to fit securely around the inhaler and extend outward to support the lever in the correct position for canister depression. To accurately match the geometry of the inhaler, I first captured the cross-sectional profile by placing the inhaler face down on the paper and tracing its outline. This tracing was then exported as an image and imported into Autodesk Fusion, where it positioned at the origin as a reference. Using this image, I created a sketch directly over the trace profile to replicate the inhaler shape within the CAD environment. This ensured that the body component would closely conform to the actual device. I then extruded the sketch outward to create the thickness of the piece and extended it along the length of the inhaler to provide a secure fit while avoiding interference with the mouthpiece and normal inhaler use. After establishing the base body, I added an extension on one side, specifically the mouthpiece side, to support the lever mechanism. This extension forms the hinge interface where the lever connects and rotates. This extension includes a recessed slot to accommodate the lever, as well as aligned holes on either side for a metal pin. This pin serves as the axis of rotation, allowing the lever to move and actuate the inhaler. The lever for our piece was also created on Autodesk Fusion. The length of the body was designed to avoid hitting the body piece. The button underneath was also designed to push down the canister on the inhaler and needed to be measured and placed correctly on the lever. The divots in the back are for the hand grip. The diameter of the grooves was determined by finding the average finger diameters. The extrusion in front was placed to eventually be attached to the body piece after 3D printing. For 3D printing, we decided to use an iterative design approach. First, we printed a shortened body component to ensure proper fit around the inhaler. Next, the body piece design was extended to fit the length of the inhaler body and connect to the lever. The first design did not have a sufficient thickness around the pinhole, and we were concerned that the extended usage would lead to the material breaking around the hinge interface. To create a more durable design, the thickness was iteratively increased and tested by attaching it to the lever via the hinge pin until piece seemed durable and secure during lever rotation. In the third piece, we tested the lever spacing relative to the body and the button alignment with the canister. We made adjustments by thickening the button and moving it forward, and we also lengthened the lever to avoid touching the body piece. After refining the design, we had the two pieces that were securely connected to each other with the pin. The pin is right here. The lever has sufficient space to rotate, as you can see, and the button of the lever, which is right here, it fits perfectly into the canister, and it can properly depress it when the lever rotates. We had one problem with just the 3D printed pieces in which they shifted upwards due to the amount of force needed to apply to the canister. Our solution was to put a Velcro strap at the bottom to secure the device in place. The overall design fit and functioned very well after the Velcro was applied. Here we are showing the easy placement of how users attach the product to the inhaler. It just slides over the inhaler and the strap gets placed below.
This is an attachment that is good for the consumers with arthritis and joint issues to use themselves.
This video demonstration shows our prototype is functional and offers a more ergonomic way to use an inhaler. In the unassisted method, the user must use 2 fingers to press down on the canister while supporting the inhaler with their thumb. This grip can be difficult for individuals with limited hand strength or joint mobility, and generating sufficient force with only 2 fingers can be challenging. With our prototype, the user places their fingers into the handholds on the lever while supporting the inhaler with their thumb. This creates a more stable and natural hand position. The user then squeezes the lever to activate the inhaler, allowing force to be applied using 4 fingers instead of 2, improving both control and ease of use. The product shown here is an existing inhaler attachment on the US market. The tall HalerMate is a direct competitor as both devices are designed for use with a Ventolin inhaler. Compared to this product, our prototype offers a key advantage through the inclusion of the hand grips on the lever, which provides greater support and control during use. Additionally, the attachment mechanisms differ significantly. The HalerMate uses a band to secure the device to the inhaler body, which may be difficult for users with limited hand strength or joint mobility to apply. In contrast, our design allows the user to slide the body piece onto the inhaler, eliminating the need for a high-resistance band and making the attachment process more accessible. Also, the HalerMate attachment extends all the way to the mouthpiece and could potentially obstruct proper inhalation during use, while our product does not have this concern. In conclusion, our prototype is a functional and competitive solution that improves inhaler usability through enhanced grip and stability. Moving forward, there are several key areas for improvement and further development of our design. First, we plan to conduct consumer testing with our target user populations to gather feedback on usability, comfort, and overall effectiveness. In addition, we aim to quantify the performance of our design through force and usability testing, which will allow us to validate how the device improves ease of use. We also plan to identify optimal materials that provide the right balance of durability, comfort, and functionality for long-term use. From a design perspective, a major improvement will be integrating a secure base attachment directly into the device to eliminate the need for Velcro. Finally, we would like to expand compatibility to a wider range of inhaler types and develop multiple lever sizes to better accommodate different hand sizes. Together, these improvements will help transition our prototype into a more refined and user-ready product.
We would like to thank the DFX Lab for the 3D printing training and resources needed for this project. Thank you.